virtual talk because Ron couldn't make it here, but we are very grateful he can do it via Zoom. So if you have questions, just raise your hand. Anyways, I'm going to interrupt him, and we can have the discussion that way. He can hear us in the microphone. All right. So thanks, Ron, and I think we can get started.
Okay, thank you. And thank you for the invitation. I always enjoy these small workshops much better than the big conferences. The discussions are much more productive, but unfortunately, I couldn't be there, couldn't make it this time. Okay, so I'm going to present a number of applications of the regularity lemma to graph machine learning. And the applications are going to be both for deriving theoretical results and for deriving practical computational methods. Okay, I'm mainly going to focus on 3 papers with these collaborators. So let's start with the motivation from the point of view of the theoretical results. And we want to prove theoretical results for graph neural networks like generalization theorems and maybe universal approximation theorems. If we compare the situation to more classical neural networks like multi-layer perceptrons or convolution networks, these are functions that map vectors from Euclidean spaces to vectors. And the fact that you have a regular structure, namely the Euclidean metric in the input space and the output space, allows you to prove theorems like universal approximation, which shows that any continuous function can be approximated by a neural network, or generalization theorems, which show that if you train a neural network, then you're guaranteed that the test accuracy is close to the training accuracy. And for proving all of these results, you use the metric properties of the input space. Right? For example, you use compactness or covering number by how many balls of a certain radius you need to cover the whole space, continuity of functions, Lipschitz continuity, and so on. Now, if you go back to our situation, we are interested in graph neural networks. These are mappings that take graphs with node features, we call them graph signal pairs, and return either another signal on the same graph or a feature for the whole graph. And the challenge here is that in some sense, there is less structure in the space because graphs can be of any size and topology. So it is not as clear how to define a meaningful metric on the space of all graphs. So our goal is to construct a metric on the space of all graph signals, which has the following beneficial properties. First of all, the metric should be meaningful. It should have an intuitive interpretation where graphs that are close to each other should somehow represent the same phenomenon intuitively. And also the metric should have good properties that allow us to prove theoretical results. And in this talk, I'm going to focus only on generalization bounds. Okay, so what do we need out of the metric space that will allow us to prove these results? Maybe first of all, let me give you a general blueprint of the structure of the proof, which I use in many of my proofs. Antonis also showed this commutative diagram. We want to prove something on the space of graphs or graph signals. But it's difficult to prove it here because there is not a lot of structure in the space of graphs. So we come up with a mapping that represent graphs as objects in some abstract space. And in this space, we have more structure. We can define a nice metric. And we also come up with a definition of message passing network on the abstract objects, which satisfy this commutative diagram. Namely, if we take a graph and plug it in a message passing network with parameters theta, we get some output. On the other hand, if we map this graph to its abstract representation and then plug it in a message passing network with the same parameters, we should get the same output. Okay, and then we prove the theoretical result in the abstract space, and then we pull it back to the space of graphs because we have this commutative diagram. And the metric that we define here, we can pull it back to a pseudometric over the space of graphs. Okay, so what properties do we need out of the metric over the space of objects? So we are going to focus on the following theorem for generalization bound. If the space has finite covering number, namely for every epsilon we can cover the whole space with finitely many balls of radius epsilon. And in addition, all of the message passing networks are Lipschitz continuous. Then these two properties together immediately give me a generalization bound. So this is called a covering number bound or robustness analysis. You can also prove other things in this space. You can prove a universal approximation by using the Stone-Weierstrass theorem in the space of objects. Okay, now for us, the space of objects is going to be graphons. You can also choose other spaces. It's going to be graphons. I'll explain why this is a good choice. But before we continue, just I want to make sure that we understand what I mean by message passing, what type of message passing I'm using. So at each layer, we want to update every node. So each node, you plug it in a message function, right? That takes the central node and takes it takes the feature at the central node and the feature at the neighbor. You plug it in all of the neighbors, and then the central node aggregates all of the messages sent to it. And in this talk, we are going to use normalized sum aggregation. So we are going to sum all of the messages and divide by the number of vertices of the graph. Right? So this type of aggregation is mainly meaningful for dense graphs, but you can also use it for sparse graphs, and then you need to somehow scale up the message functions. Okay, and then you take the aggregated message, and plug it in the update function. And the only assumption we are going to have is that the message and update function are Lipschitz continuous, right? And you use the same message and update function for all of the nodes, and in each layer you have a different message and update function. And if you want to do a graph level task, then at the last layer you do average readout. Okay, so we are going to define the metric in the abstract space of objects, but I want to give you the interpretation of the metric when we pull it back to the space of graphs, of graph signals. So the metric is going to have the following interpretation. Two graph signals are going to be close to each other if and only if they look like they were sampled from the same stochastic block model. Okay, so there are a number of things to unpack here. First of all, what is a stochastic block model? This is a generative model of random graphs where you consider a finite set of classes and the probability of having an edge between each pair of classes. And then you randomly generate a graph by randomly sampling the vertices at the different classes and connecting each pair of vertices according to the probability from the stochastic block model. And we also assume that there is a feature value for each class that you sample when you sample the graph. Okay, so you can sample graphs of different sizes from the same stochastic block model. So these are two examples of random graphs that were sampled from the same stochastic block model. But since these are only pictures, I can also tell you that these are two deterministic graphs, but they just happen to look like as if they were sampled from some stochastic block model. Okay, so in our metric, these two graphs are going to be close to each other because they look like they were sampled from the same stochastic block model. But again, there are some things to unpack. First of all, what does it mean for a deterministic graph to look like as if it was randomly sampled? So this is something we need to define. And another thing, we are going to define a metric, right? So we need to be able to compute the distance between each pair of graphs. And for this interpretation to make sense, every graph should have some small random, every graph should have a small stochastic block model such that the graph looks like it was sampled from it. Otherwise, this interpretation of the metric doesn't make sense. So let's first of all answer the second question. Is it always possible for any deterministic graph to find a small stochastic block model such that the graph looks like it was sampled from it? And the answer to this question is yes. This is called Szemerédi's Regularity Lemma. So the lemma says exactly that. For any graph, you can partition the vertices to classes and consider a corresponding stochastic block model such that the graph looks like as if it was sampled from the stochastic block model. And the important part in this lemma is that the number of classes doesn't depend on any property of the graph, not even the number of vertices. It only depends on how much you want the graph to look random. The more you want the graph to look as if it was randomly sampled, the more classes you need. Okay, so Szemerédi proved this lemma in 78, and the lemma has many variants and many proof techniques. We are going to focus on a variant of the lemma called the weak regularity lemma that was proven by Fries and Cannon in 1999. And the lemma has many applications in pure mathematics, but I want to show you that it is also applicable in machine learning, and not even only for theoretical results, but also for computations. Okay, so we first of all need to define what it means for a graph to look as if it was randomly sampled. So we need to come up with some notations that would somehow capture statistics of edges between pairs of sets of vertices. So let's come up with some notations. For every pair of vertex sets U and S in the graph G, we denote by EGUS the number of edges between vertices in U and vertices in S. Okay, now suppose somebody gave me a partitioning of the vertices to classes V1 to Vk. Then there is some stochastic block model which best describes the graph. Okay, the stochastic block model is the one with probability. So the probability of having an edge between Vi, the class Vi, and class Vj is the actual number of edges between Vi and Vj divided by the maximal possible number of edges between Vi and Vj. Okay, so the graph is deterministic. It wasn't sampled from the stochastic block model, but if a graph is sampled from the stochastic block model, then we can compute the expected number of edges for each pair of node sets. Okay, so for each pair of vertex sets, which don't have to coincide with one of the classes, there is some formula for the expected number of edges between U of S if the graph is randomly sampled from the stochastic block model. It doesn't matter what the formula exactly says. You need to sum over all pairs of classes and count how many vertices you have from the first set in the first class and how many you have in the second class, and multiply it and multiply by the edge probability and sum everything up, and this is the expected number of edges. Okay, so now I know my graph and I know how many edges there actually are between U and S. And on the other hand, I know what should be the expected number of edges if the graph was randomly sampled. So I can compare the two values, and this would give me a definition of how much the graph looks random. So this leads to a definition called irregularity. So irregularity measures how much the graph doesn't look random. So given a partitioning of the vertices to classes, the irregularity of the graph with respect to this partitioning is the maximum over all pairs of vertex sets of the actual number of edges between U and S minus the expected number of edges if the graph was random. Right? So the closer these two values are, then the smaller the irregularity, and we interpret it as the more the graph looks like it was randomly sampled from this partitioning. And then the weak regularity lemma says that given any graph, we can always make the irregularity small. Okay, more accurately, for every epsilon, which is going to be a bound on the irregularity, and every graph, there is a partitioning of the vertices to classes, where the number of classes only depends on how much I want the irregularity to be small. It only depends on epsilon. It doesn't depend on any property of the graph, not even its size, such that irregularity with respect to this partitioning is less than epsilon. Okay, this is the weak regularity lemma. So if you followed me until now, I'm happy, because I think this is the most important thing you can take away from this lecture. So let's summarize the interpretation of the lemma. One way to think about this lemma is that even though that large deterministic graph may appear to be complicated, they are actually simple, because you can always approximate them by small stochastic block models. So I can give you pen and paper, and I can ask you to try to plot a graph that looks as deterministic as possible. but I can always take back the paper and partition the vertices to classes and show you that the graph actually looks like it was randomly sampled. Okay, so this is the lemma, and the metric is, again, it's going to have the following interpretation. Two graph signals are going to be close to each other if and only if they look like they were sampled from the same stochastic block model, and now this interpretation makes sense, right? Because for each graph signal, you can always find a small stochastic block model. Okay, but we need to extend the lemma to graphs with node features. And we also need to consider an extension to graphons. Let me explain why. If we try to directly define the metric in the space of graphs, first of all, the formula is going to be very complicated. It is much easier to define it on the space of graphons. But maybe more importantly, we are going to end up with a metric space which is not complete. We are going to have Cauchy sequences of graphs that don't converge to anything. So sequences that look as if they're supposed to converge to something, but they don't. And what we do in analysis, typically when we have a space which is not complete, we consider its completion to a complete space by adding all of the limit objects of the Cauchy sequences. For analogy, you can think about the rational numbers. The rational numbers is not a complete space. You have Cauchy sequences of numbers that don't converge to anything. And it's not, because the space is not complete, you cannot develop calculus on the rational numbers. Even the intermediate value theorem doesn't work. So what we do, we complete the space and the completion by adding all of the limit objects. And for the rational numbers, the limit space is the real numbers. And on the real numbers, this is a much nicer space, and we can develop calculus and so on. So we want to do the same for graphs. We want to consider the limit objects, and these are going to be exactly graphons. So let me give you a short reminder about graphons, even though there was a tutorial about it. So you can think about the graphon as a graph where the vertices are parameterized by a probability space instead of being parameterized by a finite set. And we simply, as the probability space, we simply take the interval 0 to 1, because as a probability space, it is quite general. It is equivalent to any box of any dimension. It is equivalent to any compact manifold. It is equivalent to any Polish space. So basically, it is equivalent to any standard probability space, which is atomless. So as a probability space, it's quite general, so it's enough to simply work with 0, 1. And the graphon can be thought of as a adjacency matrix, but for the continuum of vertices. So it is a metric, a measurable function from 0, 1 squared to 0, 1, where the interpretation of Wxy is the edge weight between vertex x and vertex y. Right? And we also assume that the graphon is undirected. So xy is equal to wyx. Okay, so we need to consider all measurable functions from 0, 1 squared to 0, 1, and these are going to be exactly all of the limit objects. Okay, so you can also think about the graphon as a generative model of graphs. This is a point of view that was discussed, I think, a lot in the workshop. In a sense, it extends the idea of a stochastic block model. You can randomly generate sample a graph from a graphon by uniformly sampling vertices at the interval 0, 1 and connecting each pair of vertices in probability Wx and Xn. Okay, now graphs can be seen as a special case of graphons. In a sense, you can embed the space of graphs in the space of graphons using something called induced graphon. So you take the adjacency matrix of the graph, when you extend it as a piecewise constant function from 0, 1 squared to 0, 1, and this is called the graphon induced by the graph. Okay, so in fact, this induction is exactly the mapping that I discussed here. This is the mapping that takes graphs and map them to graphons. It's actually not an embedding, because you have pairs of graphs. Basically, all complete graphs are going to be mapped to the same graphon. So it's not an embedding. It's just a mapping, but still it's going to satisfy this commutative diagram. It is enough for our theory. Basically, the metric here is going to induce a pseudometric here, or a metric over the quotient space with respect to the equivalence classes of graphs with distance 0. Okay, so now what we need to do is we need to extend the notion of irregularity from graphs to graphons. And it turns out that when you canonically extend the notion of irregularity from graphs to graphons, irregularity becomes a norm. Okay, and this norm is called the cut norm. So what is the definition of the cut norm? The cut norm of the difference between two graphons is defined to be the supermum over all pairs of measurable sets of vertices of the average edge density in the first graphon minus the average edge density in the second graphon between U and V, with absolute value outside the integral. In a sense, it's called cut norm because this is a cut. So this turns out to be a norm, even though the absolute value is outside the integral. If you put the absolute value inside the integral, you get the L1 norm. And turns out that this norm is not equivalent to any LP norm. Okay, now why do we say that this extends the notion of irregularity? Because in the special case where W2 is a graphon induced by a graph, and W1 is a graphon induced by a corresponding stochastic block model, then the cut norm of their difference is exactly irregularity. It's equal exactly to irregularity. Right? So this extends the notion of irregularity from graphs to graphons. Okay, so we are interested in graphs with node features, graph signals. So let's extend the notion of cut distance to graphons with signals. Now a signal is going to be a mapping from the set of vertices to some Euclidean space. Here I wrote R, but it can be R to the any power of, RD to any power D. Okay, so we define the cut norm of the difference between the two graphon signals as the cut norm of the difference between the two graphons, plus a definition of a cut norm of difference between signals. Okay, so this is like a new definition, but it turns out that, okay, so this is not equivalent to any LP norm, the cut norm of the graphon, but the cut norm of the signal is actually equivalent to the L1 norm. You can bound it from above and below by constant times the L1 norm, but still it is nicer to, so you could develop the whole theory by putting here the L1 norm, but all of the bounds and the analysis are much easier, and the bounds are smaller when you use this norm. In a sense, it is more natural than the L1 norm. Okay, so the last thing we want to do is we want to make all of the analysis invariant to permutations. So we define what we call the graphon signal cut distance. So the graphon signal cut distance between two graphon signals is the cut norm of their difference up to the best permutation that aligns the second graphon signals to the first graphon signals as best as possible. But since now the vertex set is parameterized by a probability space, it's not discrete, permutation is modeled as a measure preserving bijection. If you don't know what measure preserving bijection is, just imagine a permutation of the elements of a standard probability space. Okay, and since we extended the definition of irregularity in a natural way from graphs to graphon signals, we also inherit the interpretation of irregularity. So now we can interpret the cut distance between two graphon signals as how much these two graphon signals look like as if they were sampled from the same stochastic block model. Okay, so this is the metric that we are going to work with in the space of graphon signals. And now we managed to extend the weak regularity lemma to graphon signals. Okay, so now the lemma says that for any graphon signal and every epsilon that now is going to be a bound on the cut distance, which is equivalent to irregularity, there exists a piecewise constant graphon signal, namely a stochastic block model, such that the cut distance between the graphon signal and the stochastic block model is less than epsilon. Now, the nice thing about this version of the theorem, this variant of the regularity lemma, is that it's not only that the number of classes only depends on epsilon. So the number of classes doesn't depend on the graphon signal, but not only the number of classes don't depend on the graphon signal, but also the classes themselves don't depend on the graphon signal. Because all of the analysis is up to permutation, you can always arrange the classes to be exactly the intervals. And they are predefined, right? Given the number of intervals, the length or the intervals themselves are unique. And this, in fact, means that we managed to approximate the space of all graphon signals by a finite dimensional space, right? Because the space of all piecewise constant functions over a given partition, which is predefined, is finite dimensional. And this leads to the compactness of the space of graphon signals. Right? But before I formulate the theorem about compactness, let me illustrate the theorem. So here we have a graphon signal. The graphon is plotted in grayscale over 0, 1 squared. And the signal is plotted on the diagonal in color. And the lemma says that you can always permute the vertices in such a way that brings the graphon signal to a form which can be approximated by a stochastic block model. Okay, so now, as I said before, by the fact that we managed to approximate the space of all graphon signals by a finite dimensional space, we can prove that the space of all graphon signals with the cut distance is compact. Actually, the cut distance is a pseudometric, but you can always consider the quotient space of graphon signals up to modulo graphon signals of distance 0. Okay, so the space is compact, and we can also come up with a bound for the covering number. So if you want to cover the whole space by balls of radius epsilon, you need this many balls of radius epsilon. Okay, so this is nice because we took the space of all graph signals, which seems like a very big space, right? It's definitely not finite dimensional because graphs can be of any size. And we managed to show that it is actually not a big space because it is dense in a compact space. And a compact space is interpreted as a small space, right? Okay, so, but this statement is only useful if the metric that we derived is somehow compatible with the functions we are interested in, with message passing networks. So think about the following extreme example. If I just want to make the space compact, I can simply take the trivial metric or the trivial pseudometric in which the distance between each pair of points is 0. And then obviously the space is compact, but this metric is not useful for anything because no function can be continuous with respect to this metric, except for the constant function, right? So the next thing we want to show is that this metric is actually compatible with message passing networks. So we want to show that message passing networks are Lipschitz continuous with respect to cut distance. First of all, we need to define what we mean by message passing on graphon signals, because message passing is usually defined on graph signals. There is a canonical extension of message passing to graphon signals. So the extension is it's trivial, right? So first of all, the message function doesn't care if the two vertices, if the vertex has infinitely many neighbors or finitely many neighbors, right? The message function, you only plug in two values in it, the value of the central vertex and the value of a neighbor. So this is trivial to extend. The only thing we need to extend is aggregation. And then it is quite easy to see that the canonical extension of normalized sum aggregation to graphons is integral aggregation. You take all of the messages and you integrate them against the graphon. So why is this canonical? Because it satisfies the commutative diagram. If you take a graph signal and you induce a graphon signal from it, on the one hand, you apply normalized sum aggregation on the graph signal. On the other hand, you apply integral aggregation on the graphon signal, and then you need to also induce a graphon after aggregation, you get exactly the same thing. Right? So this is the canonical definition. And now that we have a definition of message passing networks, we can prove Lipschitz continuity. And the only thing we need to assume is that the message functions are Lipschitz continuous. And under this assumption, we managed to prove that message passing networks are Lipschitz continuous. Namely, given any two graphon signals, if you plug them in a message passing network, and then compute or evaluate the distance between them, this is bounded by the distance between the two graphon signals up to a constant, which depends only on the Lipschitz bounds of the message functions, right? So this is, we got Lipschitz continuity. Now, if you think about it, this is somewhat similar to, so most of this is in a sense stability result. And most of the papers that you will see in graph machine learning about stability results always assume a generative model for the graph. They assume that the graph is sampled from some random graph model, for example, from a graphon. And under a model of the data, they show some stability. Now, what we show here is that you don't need any model of the data. You always have this Lipschitz continuity for any two pair of graph signals or any two pair of graphon signals. In a sense, you don't need to assume that the graph signal is sampled from a graphon because the regularity lemma says that any graph signal looks like as if it was sampled from a graphon. So in a sense, this is the intuition behind it. But the nice thing about this construction is that you don't need any assumptions whatsoever on the data distribution and on the number of parameters and anything at all. Okay. So in a sense, so we managed to prove that the space of graphon signals is compact under some metric that we derived. And in addition, message passing networks are Lipschitz continuous. In a sense, these are two competing properties, and we managed to prove both of them because making the space compact means that you need to find a metric in which all of the points are close to each other. On the other hand, if all of the points are too close to each other, then it's more difficult for functions to be continuous, right? But still, we managed to prove these two things. And then these two properties together, and specifically the fact that we have a finite covering number and the message passing networks are Lipschitz continuous, immediately gives us a generalization theorem, right? That says that you are guaranteed that if you train a network on a training set, the test accuracy is close to the training accuracy, where the difference between them goes to zero as the training set goes to infinity. The good thing about this version, this generalization theorem, is that you don't need any assumption whatsoever about the data distribution. It works for any distribution of graph signals or graphon signals. The distribution can also be supported only for graph signals, right? So it can be just a standard data set. And you don't need any assumption also for the loss function. So it's quite a general result. So there are additional theoretical results that I want to skip because what I want to show you is that we can also use the weak regularity lemma for practical computations on graphs. Let me give you the motivation. And this, I think this is interesting because most people think about the regularity lemma as a tool for analysis. And here I'm showing that it is also a good tool for computations. So the motivation is as follows. Often, we want to process very large graphs. For example, social networks can have hundreds of millions of vertices and orders of magnitude more edges. And it is impossible to fit such data in the GPU and train a standard neural network on such a big data set. So what people typically do is they subsample the graph with different strategies. But on the other hand, if you think about it, the regularity lemma says that in some sense, there are no large graphs. Every large graph can be approximated by a small stochastic block model. So why not, instead of processing the large graph, let's instead process the data in the stochastic block model that approximates it. And then we can be completely scalable because the amount of information can never go to infinity when you take the graph, the size of the graph to infinity. So this idea actually works. We implemented it, and it gives good accuracy, and it's also very efficient. But there are many challenges, so it's not straightforward. Let me give you some challenges. So first of all, the weak regularity lemma that I presented to you is not constructive, right? It only says that given a graph, there exists a partitioning of the vertices to classes. It doesn't tell you how to compute this partitioning. So actually, the first paper by Fries and Cannon from 99 did propose an algorithm, but this algorithm is not useful in practice. It is exponentially slow in the number of classes. It's only good for theoretical analysis, but not for actual computations. So we need to somehow come up with an efficient way to estimate the approximating stochastic block model. And the other challenge, which is quite big, is that the asymptotics in the regularity lemma is terrible, right? If you want to approximate your graph up to error epsilon, then you need 2 to the power of 1 divided by epsilon squared classes. So for moderately small epsilon, this number is going to be huge. It's going to be much larger than the number of vertices, and then the whole approximation is going to be pointless. So we also need to address the problem with the asymptotics. And let me first of all tell you how to solve the problem with the asymptotics, because it's actually well known that if you allow the classes to overlap, to have intersections, then you don't need to be exponential in 1 divided by epsilon squared, but the number of classes are actually linear in 1 divided by epsilon squared. So this is actually a part of the proof of the weak regularity lemma. You first of all construct overlapping communities, C divided by epsilon squared overlapping communities, and then you take all of the intersections between them to get non-overlapping communities, and this is why you get 2 to the power of 1 divided by epsilon squared. Okay, so now we want to work with overlapping communities. So let's consider graphs. Let's call these graphs intersecting community graph signals. So these are graph signals of the following form. You consider a set of classes of, a finite set of classes of the vertices, and you consider the clique of each class and the linear combination of the cliques, and this is your intersecting community graph signal, ICG. And the signal is the linear combination of the indicator functions of the classes, of the same classes. Okay, so now we want to optimize, we want to fit an ICG to a given graph, and to be able to optimize the community structure, we need the affiliation of each vertex to each class not to be binary, 0 or 1. We need to relax it to be continuous, right? So we need to so each vertex now it's not as if it is either affiliated or not affiliated to a class. You have how much the vertex is affiliated to each class. Okay, and then we call such a model, such a class of graphs, soft intersecting community ICG model. Soft intersecting community model, right? It's a linear combination of these soft cliques, if you like. And now we want to fit such a graph to my given graph. But I want to discuss another challenge before I show you how to optimize this ICG. And this challenge is about density. So in a sense, the weak regularity lemma is mainly meaningful for dense graphs. What do I mean by that? If you take a graph, so you can pull back the definition of cut norm from the space of graphons to the space of graphs using induction, right? So if you do that, then the cut norm of a matrix, of a difference between two adjacency matrices, is the sum of all of the edge weights, or the difference between the edge weights. And because you integrate in the graphon space, what you get is division by n squared, right? Because the more vertices you have, the smaller the intervals in the induced graphon. So the formula for cut norm over the space of graphs is the sum of all of the supernorm over all of the cuts of the sum of the edge densities divided by n squared. And then if you want to evaluate the distance between two sparse graphs, the distance is always going to be close to 0, because the number of non-zero edges, the number of non-zero weights, is going to be much smaller than n squared. N is the number of vertices. So this metric is not going to be meaningful. All of the sparse graphs are going to be close to zero. So what we need to do is we simply need to renormalize this normalization term. So instead of normalizing by n squared, we normalize by some characteristic number of edges that we expect to see in our graphs. And for the signal, there is no need to normalize in a special way because the signal is not sparse. Okay, and then we managed to prove the following variant of the weak regularity lemma, which has a constructive flavor. So the theorem says the following thing. So we have our graph signal. A is the adjacency matrix, S is the signal, and we want to approximate it by an ICG, an intersecting community graph signal. So in principle, we are supposed to minimize the cut norm. But there is a problem here because, first of all, computing the cut norm is NP hard. But even if you ignore this, and you somehow try to implement some numerical algorithm with brute force by doing gradient descent on this difference, you're going to end up with a problem because the definition of cut norm involves maximization. It's the maximum over all of the cuts, and you want to minimize it. So you're going to end up with a min-max problem, which simply doesn't work numerically. If you try to minimize it with brute force, you get junk. So we cannot directly minimize the cut norm, but instead what we show in the theorem is that you can minimize the Frobenius distance between the graph signal and the ICG. This is much easier to do. You can use gradient descent, and you can also utilize Dirac decomposition of the graph signal using the best rank K approximation theorem and so on. And what the theorem says is that if you minimize the Frobenius error and you manage to find a close to optimal ICG, then you are guaranteed that the cut distance is small. So I want to emphasize that the optimal Frobenius error is not going to be small because we are trying to approximate a granular adjacency matrix or a sparse adjacency matrix by a low rank intersecting community graph. It is impossible to make the distance between a sparse graph and a low rank graph small in Frobenius norm. So this minimal distance is going to be large in Frobenius norm, but it doesn't matter. As long as I got close to the optimal distance in Frobenius error, I'm guaranteed that the cut norm is small. Now, because now we work with sparse graphs, we have some term here which depends on the sparsity level. So the sparse, we no longer have the property that the number of communities only depends on the accuracy. Now the number of communities also depends on the sparsity level. So this is a problem because we often want to work with sparse graphs. So in a follow-up paper, we managed to get rid of the dependency of the sparsity level, and we can actually bound the error by so the number of required communities for a given error only depends on the error, not on the sparsity level, not on the size of the graph, not on anything, only on the accuracy. And the way we do it is we replace the metric, the cut norm, by a weighted version of the cut norm, and we replace the Frobenius norm by a weighted version of the Frobenius norm, which gives less weight to the non-edges. So basically, I'm focusing more on the connectivity structure than the non-connectivity structure, and by doing this, effectively minimizing this weighted Frobenius norm is going to densify the graph. I'm going to find approximating intersecting community graph signal, which is a densified version of my original graph. And then I'm guaranteed that the cut distance is small. Now, if you think about it, it's nice to think about it that usually when people work with very large graphs and they want to do something efficient, they sparsify the graph. They get rid of many edges and get rid of many vertices. We say that you can also do the exact opposite. You can densify the graph to make computations more efficient, which is a bit counterintuitive, but this is what the theorem says. Okay, so now we can approximate our graph signal by an ICG. And instead of processing the graph signal, we can directly process the community structure. So this is what we did. And then the neural network has complexity, which is linear in the number of vertices instead of linear in the number of edges like message passing networks. So this is much more efficient for large graphs. And we ran it on benchmarks, and we got very nice accuracy, and it's also very efficient. I'm going to skip the benchmarks because I don't think it's very interesting. Okay. So this is one or two applications. I'm going to skip the rest of the practical applications. So let me summarize. So I showed you a few applications of the weak regularity lemma. So first of all, we wanted to prove generalization bound. The weak regularity lemma says that in some sense, every large graph looks like it was sampled from a small stochastic block model. And using the weak regularity lemma, you can construct the graph on signal cut metric, and under which the space of all graph signals is dense in a compact space. And also message passing networks ellipse is continuous with respect to this metric. And from this, you can prove a generalization bound. And you can also use the weak regularity lemma for processing very large graphs efficiently. Okay, so if you're interested in this line of work of using the weak regularity lemma in graph machine learning, these are my works that derive theoretical results using the weak regularity lemma, and these are my works that derive practical computational methods, and also theory to support these methods. So maybe if I have, do I have a couple of more minutes?
Yes, you have.
So maybe if I have a couple of more minutes, I want to maybe end with a message that I think, first of all, one message is that I think the weak regularity lemma is not only a tool for theory, it's actually a practical tool. You just need to formulate it in such a way, then it can be useful for practical application. And there's another thing that I want to tell you, which I think is quite interesting, quite important, if you want to get into using graphon theory for graph machine learning. So the definition of graphon is a measurable function from 0, 1 squared to 0, 1. And when you do graphon theory, you should only treat it as a measurable function. You're not allowed to use tools from calculus. You're not allowed to use a metric structure over 0, 1. And the reason is that if you want the domain to be general, 0, 1 is only general as a probability space because it's equivalent to any other standard probability space and to any Polish space. Now, if you read many papers, they treat graphons using tools from calculus. They assume that the graphon is continuous or smooth or Lipschitz continuous. And when you do that, you're not really doing a theory of graphon analysis. You're somehow combining, or you're doing more of a mathematical modeling. You're coming up with a model that you think that graphs from reality behave like this model. They behave as if they were sampled from some graphon, which is Lipschitz continuous. The problem is that the set of Lipschitz continuous graphons with uniformly bounded Lipschitz constant is a meager set. It's lower dense, so it's almost like a pathology. If you want to think about graphons as all of the limit objects of graphs, then you have to take all of the measurable functions. You cannot assume any, but it's still fine to assume a generative model, but then you're not really doing graphon theory. And then you also need to extend the dimension of 0, 1, because as a metric space, it's not general at all. It only describes one-dimensional thing. So if you assume that your graphon is Lipschitz continuous over 0, 1 squared, and you assume all graphs are sampled from this graphon, basically what you assume is that your graphs describe only one dimension. They are basically one-dimensional geometric objects. So if you want to go in the route of building random graph models, you should increase the dimension here. For example, you should take it as a general metric space with a general Minkowski dimension or something like that. Okay, so that's my message is that if you develop theory using graphons, think about the assumptions you take on the graphons. Are they general enough And what do they say about what you think about data from real life? Okay, so that's basically what I wanted to say. Thank you for the attention.
Thank you. Are there any questions? Yes, I'll get you the mic.
Hi, Ron. Thank you very much. Teresa here. I don't know if you can see me, but thank you very much for the talk. Can you give a bit more intuition at the end where you say you densify the graph and then that actually lead to computation efficiency gain? Where,
Yes.
yeah, is it instead of the common wisdom where you maybe make the graph sparser?
Yes.
Can you, remark a bit more? Thank you.
Definitely. So in this variant of the weak regularity lemma, we try to minimize a weighted version of cut distance where, in cut distance, you need to sum over all of the edges. Now we multiply each edge by weight. So you need to sum all of the entries of the adjacency matrix, the edges and the non-edges. And the non-edges of the graph, we multiply by a small weight. And this means that the metric it gives more emphasis to the edges than to the non-edges of the graph that I'm trying to approximate, by definition. And then when you minimize this Frobenius norm, what happens in practice is that because we are trying to approximate a sparse graph signal by a low rank graph signal, and we don't care so much, we care less about what happens to the non-edges, we care less about approximating the non-edges than the edges, then what happens in practice is that you end up with a graph signal which is denser than the original graph signal that you try to approximate. So you have many more edges, but it is still efficient to do it because the data structure doesn't care. The data structure of this graph signal is not modeled as a matrix. It is modeled as a linear combination of these cliques. So you only need to model functions or vectors which are n-dimensional. So this is still efficient. Even though you densify the graph, you actually replace the original sparse graph with a more efficient model of a dense graph. And then you can do all of the downstream computations on this densified version of the graph. And you can do it very efficiently because you directly operate on the structure of the communities instead of operating on the adjacency matrix or the sparse representation of the graph. So this is another option for working with large graphs. You don't have to densify them. You can also you don't have to only sparsify them. You can also densify them.
Thank you. Thank you. So my takeaway is you kind of replace sparsity with low rankness.
Yes.
And okay, nice. Thank you very much.
Thank you. Any other questions? All right, we have a few more minutes. Actually, I had one practical question. So I think this is very interesting that you can use the regularity to actually compress the graph in a sense. In practice, how do you choose the number of components in there? So, I mean, it's probably empirical. You get a rough estimate.
Either you use this bound,
yeah.
Right? But I mean, if you know that you want some accuracy, then you know how many communities to use, or this is just a hyperparameter that you search through.
Yeah.
You basically have the number of communities as a hyperparameter, and that's it. You don't have so many hyperparameters when optimizing the ICG.
Yeah.
So you can simply search with one-dimensional grid search or something.
Yeah, nice. Okay, if there are no further questions, then let's thank the speaker, and then we'll have a lunch break until 1:30.
Bye.
Thank you, Ron.